trying to solve a really complex mathematical equation, maybe something with x to the power of 14 or, even higher, it can feel like hitting a brick wall.
Absolutely. And traditionally, for these really high degree polynomials, the go to methods often give you, well, an approximation.
Right, something close, maybe very close, but not that perfect exact symbolic answer.
And that's been a big sticking point. I mean, classical algebra, things like Abel's theorem, even suggested that for degree 5 and up, you often couldn't solve them exactly using radicals.
So the question was kind of hanging there.
Right.
Are exact answers just impossible for lots of these?
Pretty much, yeah.
Okay, well, this deep dive is looking at something that challenges that idea. We've got a source here talking about Ezouidi's theorem,
And this theorem claims to offer a way to find those exact symbolic solutions.
which is pretty bold. It suggests bypassing those classical limitations and numerical workarounds.
Exactly. It aims to reveal the precise roots, not just estimate them.
And the source really puts it to the test. It tackles a beast of a problem, a 14th degree polynomial.
It's quite the example.
So our mission today is to unpack this theorem, see how it works on this monster equation, and understand how it finds those exact solutions. Okay, let's get into it.
Sounds good.
So maybe let's start with the old way. You mentioned numerical methods having limitations. If you use something like, say, Newton's method, what's the main issue?
Well, the thing is, they're iterative. You start with a guess, refine it again.
Going closer each time.
Exactly, closer and closer. But the end result is usually a decimal number, approximation.
Right. You can get rounding errors, things like that.
You can, especially with complex calculations. And
Mhm.
fundamentally, you don't end up with that clean, mathematically perfect symbolic form of the root.
Like getting 3.14159 instead of just dot pi.
Precisely. And you add that to the classical idea that maybe you couldn't solve many of them with radicals anyway. It
Yeah.
felt like a hard limit.
Okay, so that really sets the stage for why this theorem is interesting. What's the core idea behind Ezouidi's theorem? How does it find exact solutions?
The key idea is a transformation. Instead of wrestling with the polynomial's original coefficients directly,
The numbers multiplying the x's.
right, the theorem expresses the polynomial using a different set of symbolic coefficients. The source calls them SK1.
Okay, so new coefficients is coefficients, and the theorem tells you how to find these.
Yes, it provides a systematic step by step way to calculate these is coefficients from the original ones.
So it's like changing your perspective on the polynomial, looking at it differently.
That's a great way to put it. And this news is perspective can sometimes uh, reveal a much simpler underlying structure.
Interesting. Okay, let's make this concrete with the example. The source uses this very long polynomial. Let me see if I can read it out.
Go for it. It's a long one.
Px equals 14 bugumi plus 91 in Yumi plus 364 bugumi plus 2002 in Yumi plus 3003 venio plus 3003 up euro plus 3003 in June plus 3001 in Urim plus 1001 in Yumi plus 155 Elio plus 65 in 2.
Phew. Yeah, that's it. 14 terms, degree 14.
Quite something. Now, the source mentions right away that x1 is actually a root here, twice over, a multiplicity of 2.
Yes, that's a known starting point they provide, and we'll see how the method sort of confirms it later.
It defines the original coefficients, the numbers like negative 14, 91, negative 364, and so on, using L notation, 0 through L13.
That's right. So L1 is 91, L2 is 364, all the way down to L13 being 65. These are just the standard coefficients from the equation you read out.
Okay, got it. The familiar numbers.
And Ezouidi's theorem uses these L values as the input to calculate those new C's coefficients we talked about.
And you mentioned a recursive formula. How does that work?
Yeah, recursive. The source gives the formula. Basically, to calculate any given SK1, you need the degree n, which is 14 here, the first coefficient L of 0, which is 14, some binomial coefficients, and crucially, the D's values you've already calculated before it.
Ah, like nesting dolls, you said. Each one depends on the ones inside.
Exactly. You calculate 0 first, then you use that to help calculate S1, then you use 0 and S1 to help calculate S2, and so on. It's a systematic buildup.
Okay. Methodically work your way through, calculating 0, S1, S2, all the way up to S13 for this 14th degree case.
You got it. And the source shows the results of doing this calculation for the specific polynomial. And here's where it gets really interesting.
What happens?
Most of them turn out to be 0.
0 for that complicated starting polynomial.
Yep. The calculations show S0 is 0, S1 is 0, all the way up to S10.
Oh.
And then S12 and S13 are also 0.
So it's like this as perspective just clears out almost everything.
It's an incredible simplification. This pattern of zeros is the key insight revealed by the transformation.
So which coefficients aren't 0 then?
Just one, actually. The calculation finds that S11 is the only non-zero one in this range.
And what's its value?
It comes out as 64 times 14 raised to the power of 12, a specific calculated value.
Okay, so we have these coefficients, mostly 0, with S11 being non-zero. How does that link back to the polynomial equation, PSO?
Well, remember, the theorem lets us rewrite px using these as coefficients. The general form given is px SO0 xco plus S1 x0 plus S13 and so on, alternating signs, all the way to plus S11 x whole s plus S13 are 0.
I see where this is going. So it's 0 through S10 are 0.
And S12 and S13 are 0.
All those terms just disappear.
They're like that massive, intimidating 14-term polynomial collapses. You're left with just pxx, SO11 xsa equals 0.
Incredible. From 14 terms down to just 2.
Yeah.
That really shows the power of this coefficient perspective.
It really does. And we know S7. So substitute that value in. X Ezo plus 64 plus 16x0 is 0 equals 0.
And that looks much, much easier to solve.
Absolutely. You can factor out excess straight away.
Giving you excess sedge times excess plus 64 is plus 13 times 0.
Right. So for this whole thing to be 0, either the x over part must be 0 or the part in the parentheses must be 0.
Okay, x equals is easy. That means x is caret.
And since it was x squared, that root xe0 has a multiplicity of 2. 2 of the 14 roots are 0.
Okay. What about the other part? X cetera plus 64 times 14 roots equals 0.
That means we need x root to equal negative 64 meter under 14 roots.
That's right. Taking an even root, the 12th root, of a negative number, that means complex numbers are involved.
Precisely. The solutions aren't going to be simple real numbers. You need to use tools from complex analysis. The source mentions using complex exponentials like e to the power of something involving I and pi.
Those things that help map out numbers in the complex plane.
Exactly. They allow you to find all 12 distinct complex roots for x third equal to 64, y 14 wadgers, and 4 time. It's the standard way to find roots of complex numbers.
And when you apply that method,
the source gives the result. The exact symbolic solutions for these 12 roots are xk equal 14 times the square root of 2 multiplied by e raised to the power of 2k plus 1 times I times pi divided by 12.
Okay, so that gives you 12 specific exact symbolic roots in the complex plane, plus the 2 roots at x0 we found earlier. That's all 14 roots.
It's all 14.
And what about the x1 root that was mentioned at the start? Does the theorem account for that?
Yes. The source shows a separate calculation. It uses a related formula, el Eroclestato, for the specific complex roots corresponding to key 0 and k1. When you plug them into this alpha formula using L0 to row 14, the result simplifies down to u go 1.
So the theorem's results, through this extra step, confirm that x1 is indeed a root. And since it works for 2k values,
it confirms the multiplicity of 2 for the root x1, matching the initial information provided. It all ties together.
Okay, let's pull back a bit. What's the big picture here? Why is this result, using Ezouidi's theorem on this 14th degree polynomial, so important?
I think the crucial thing is the exactness. We're not talking about approximations from numerical methods anymore.
Yeah.
This theorem, at least in this case, delivered precise symbolic expressions for every single root. No rounding errors, no close enough.
And that directly challenges the old ideas, maybe stemming from Abel's theorem, that exact solutions just weren't generally possible for high degrees.
It certainly suggests that there might be ways to find exact solutions, even when classical methods using radicals hit a wall. This transformation into Pi's coefficients seems to be a key step, revealing solvability.
A hidden structure made visible.
Something like that, yes. And the source points out you could, in theory, plug any of these exact symbolic roots back into that original massive polynomial.
The Esquio minus 14 by I about 1.
Right. Plug them back in, do the complex arithmetic, and it would equal 0 perfectly. Verification.
That's pretty compelling. And you can immediately see why this matters. Think about fields like, I don't know, aerospace engineering or fundamental physics.
Or even cryptography.
Right. Places where getting the exact answer versus just a very good approximation could be critical. It's the difference between knowing precisely where something is and just having a really good estimate.
It opens the door to analysis and applications that maybe weren't feasible if you only had approximations to work with.
So it leaves us with a really interesting question to chew on, doesn't it? If this theorem can unravel a complex 14th degree polynomial and give exact answers through this specific approach, well, How many other mathematical problems out there, problems we currently rely on approximations for, might also have exact solutions just waiting to be found?
Maybe through this method, or perhaps through other new theoretical lenses we haven't discovered yet.
What does it mean for the future of maths when these long held assumptions about what's solvable, what's not, get challenged like this? It makes you wonder what other hidden exactness might be out there.
It definitely suggests that even in very old fields like algebra, there can still be surprising and fundamental breakthroughs. It keeps things exciting.